Heat generation is nothing but conversion of any other form of energy into a thermal energy inside the body, right? So like we have uh, said previously also that in case of electric wires, when current is flowing through it, some of the electric energy is converted into thermal energy. And in case of nuclear rods, nuclear energy is converted into thermal energy. Some part of it's converted into thermal energy that heats the rod, and that is used for generation of power in case of nuclear power plants. In case of our body, um, chemical energy is converted into thermal energy when metabolism starts. Okay, in general, in reality, heat generation is a non-uniform phenomena. Okay, it means that at every point at every point in the body, the heat generation is non-uniform. Means if it is 20 watt per meter cube at this point, it may be 30 watt per meter cube at this point. But for simplicity of the subject, we are assuming that heat generation is uniform throughout the body. So it means that at every point there is same value of heat generation. Okay, so we will derive the temperature distribution for the case of plane wall, then for means solid cylinder, and then solid sphere. That will be the flow of lectures for the case of heat transfer when there is generation of thermal energy. So excuse me. So what are the assumptions? As we have seen till now, the various assumption will be like steady state heat transfer, right? One dimensional, because we are assuming heat transfer only in this x coordinate, right? In this direction only. One dimensional steady state, and material is homogeneous and isotropic. K value is constant. We are assuming K value is constant here. Okay, but we are relaxing some other assumption, which is nothing but the no heat generation we saw in the last lecture. So in this lecture we are assuming that there is uniform heat generation. So this is the extra assumption we are making here. So fine, and consider the plane wall as shown here, and consider the control volume around it, and assume that on both sides of the plane wall different fluids are there, and uniform value of heat generation is present inside the body, which is a source which is generating the heat inside the body at this rate, watt per meter cube. Okay, and as we have seen already before also, that heat generation is a volumetric phenomenon, right? So to find the temperature distribution for a plane wall when it is subjected to different fluids on both sides, and because of the different fluids, heat transfer coefficient and free stream temperature on both sides will be different. On left hand side H1 T infinity 1, on right hand side H2 T infinity 2, right? And consider that the left section is at x is equal to 0 and the right section is at x is equal to L, right? So we have to find the temperature distribution for this case. So we cannot start from the Fourier law here, because if we consider between two sections, heat is not same. Why? Let's see these are the two sections, like this section and this section, these two sections. So let's say Q1 amount of heat is entering in this section and Q2 amount of heat is leaving this section. So let's say that let's apply energy balance between these two sections. So Q in minus Q out plus Q generation is equal to Q stored. Since it is steady state, means this term will be 0, because it is present only in case of unsteady state. And Q1 is entering, Q2 is leaving, but some amount of heat is generating between those two sections, right? And which is nothing but Qg times the volume of between these two sections, right? Let's call this volume dV. So Q1 is not equal to Q2. So we can apply Fourier law at particular section but not for whole body in this case, because heat is not same at every plane. But in the previous section what happened, there was no internal heat generation, that's why Q1 was Q2. If there is no heat generation, then Q1 equal to Q2, because there is no internal heat generation between the 2 points inside the body. That's why, so we have to start with the governing heat equation, which is nothing but, for one dimensional case we can like that, we can write like this. Okay, and since it is steady state, so this term will be 0. So first term is diffusion term, the internal heat generation term, and this is the unsteady term, right? So one dimensional case, temperature will be function of x only, right? It means we can write this partial derivative as an ordinary derivative, and this is constant because it is uniform heat generation. So it is a second order ordinary differential equation. For second order ordinary differential equation, we need two boundary conditions to solve this, right? So if we integrate it for first time, we will get dt by dx as minus qgx by k plus c1, right? And if we integrate it one more time, we get the temperature distribution inside this body. We can see the temperature is dependent on the minus x square, is proportional to minus x square. So it will be some parabola like this, because parabola facing downward, right? Okay, so for solving this, because there are two arbitrary constants c1 and c2, we need two boundary conditions. So at x is equal to 0, let's say t is t1, and x equal to L, t is t2. So applying this, x equal to 0, if we put in this second equation, x equal to 0, first term will be gone, second term will be gone, so t1 will be equal to tc2. So c2 we get as this. So if we plug in this c2 value in the second equation, as we can see here, we get this equation, this. Okay, and if we apply the second boundary condition, that is x equal to L, put x is equal to L here, so minus qgl square divided by 2k plus c1l plus t1. So we can get t1 as this value. So putting c1 in the above equation, this second equation, so we can get a temperature profile like this, right? So we have the temperature profile for this case. Right, so temperature will look like this temperature profile if we plot on this graph in this body. So it will look like this. Maximum temperature, we don't know that where maximum temperature will occur. Okay, it is downward facing parabola, and how? Because at x equal to 0 some t1 temperature, and x equal to L some t2 temperature, and because of heat generation, the temperature inside at every point will increase. And since it is downward, so as we increase, as we keep on going forward, so the temperature will again decrease because downward facing parabola, but we don't know where the maximum temperature will occur. So we have to find this location, at which location maximum temperature will occur. Okay, so for location of maximum temperature, differentiate that our equation by first time and put equal to 0, right? So we have already have this term, so dt by dx is 0, so minus qgx divided by k plus c1 equal to 0. So x we can have c1k divided by qg, and c1 we know what is c1, k by qg times c1. c1 is this value, t2 minus t1 plus qgl by 2k, t2 minus t1 by l plus qgl divided by 2k. Okay, so if we rearrange it, we can have L by 2 minus K by Qg T1 minus T2 by L. So if maximum location of maximum temperature depends on T1 and T2 values, right? So if T1 is greater than T2, right, it means this quantity will be positive, and because of that x will be less than L by 2. It means the maximum temperature will occur left of x equal to L by 2. Okay, so this will be the maximum temperature location, right? And we can find the maximum temperature also, that what will be the value of this temperature we can find by putting this value in this equation. We can find what is the maximum temperature inside the body, right? And these walls, these two walls, T1 and T2 walls, will have higher temperature or lower temperature, depends on the fluids they are facing, right? Let me explain you what I mean by that. So this side, if this side fluid has less heat transfer coefficient, means less ability to conduct away heat from this body, right? Okay, so if this side, left hand side fluid has less ability to conduct, less ability to take away the heat from the hot body, then the left side will have higher temperature, and vice versa for the right hand side. That means that this side has higher heat transfer coefficient, means higher capability to take away the heat from the right hand side plane. It means the temperature will be lower on that side. Okay, so that is the case. So H1 and H2 are the influencing factors for values of T1 and T2 on both sides of the plane. Alright, so if we want to find what is the T1 and T2 on both the sides, we can apply the energy balance for this thin line, the wall on the right hand side. So Q left hand side, so minus Ka dt by dx at x equal to 0. Okay, and this will be the heat thermal conductivity of the body, and that heat conduction will be taken by the fluid, so it will H1A times T1 minus T infinity. So we know temperature profile, so we can find dt by dx at x equals 0. We know K and A all are given. So let's say H1 is also given, so we can find what is the value of T1. Similarly on the right hand side, minus Ka dt by dx at x equal to L H2 times A T2 minus T infinity 2. So we can find the T1 and T2 values. All are